Hi again. We'll try to solve this question from topic beams, shear force, and bending moment diagrams. So the question is one of the questions from your quizzes. Draw the shear force SF and bending moment BM diagrams for this application. So you have a support reactions at RA, support reaction at RB, and then you have a 5 kilonewtons about 1.5 meters away from that end, the left ends. UDL load 7 kilonewtons per meter, covering about 5 meters length. And from here to there is 3.5 meters, and that's 5 kilonewtons away from the right side, about 1.5. So this kind of questions, the first step you start is step 1 is the free body diagram. Since we have the support reactions in that way, so we need to calculate the support reaction. So step 1, find the free body diagram. In this case, we allocate the UDL load at the center. So we find the middle of 5 meters is 2.5. 7 is the load times 5, which is the distance. You get 35 kilonewtons. So it's mean in the centroid we'll have the weight of that UDL. And now second step, step 2, we need to calculate the values for RA and RB. So how we do that? We learned from non-concurrent forces, so you can take two equations, algebraic summation of forces in the y directions, and we take a moment about points, let's say at A. So let's start with the first step. Algebraic summation forces on the y direction upwards is positive. So what you have RA and RB in one side going up equals to what? The opposite of that, you have the 35 kilonewtons is the weight of the UDL, and 5 kilonewtons here and 5 kilonewtons. So this will be calling it equation 1. RA plus RB is equal to 45. And then we need to take the moment around the points, and we assume clockwise is the positive about point A. So RB will be rotating in that direction, and that's mean negative, minus RB. Now the distance from here to that point A is 1.5 plus 3.5 plus 5 meters. So that's, I break it down. Plus you have 5 kilonewtons. 5 kilonewtons will rotate clockwise. Times the distance, 3.5 plus 5 meters. Plus you have the weight of the UDL, which is 7 kilonewtons per meter times the 5 meters length, and that will be here, and then times the distance 2.5. Plus, again, that's also will rotate clockwise, 5 kilonewtons times the distance 1.5. This will end up solving for you after rearranging. RB value is equal to 13.75 kilonewtons. I'll highlight it. Now we take this value and we substitute in equation 1. We'll get RA and is equal to 45 minus 13.75. So I'll highlight this again for you guys to see what we have done. Now you can work this in your when you're watching this video, and you can pause the video and you go through it. Now let's continue. Let us continue with the rest. Since we allocate these RA values, I'll put their values in the diagram. So it will be 31.25 kilonewtons, 13.75 kilonewtons. Now in this step we need to find the step 3 shear force diagram. So I already sketched the shear force diagram, but I need to explain it step by step. So first we start the shear force diagram from the left side, this one. We have the support reaction 31.25 going upwards. I just write SF represent for me shear force, kilonewtons the units. I have a horizontal line and I'm moving upwards and downwards and from point to another point. So if you see carefully, I have these disconnected lines just to represent with me where I expect to move my diagram. So we start from the left side with the 31.25, the point, and then because we have a UDL, as we learn, the UDL always will go to slope. So we move from the UDL till that point here. How can I resolve that? I need to take a section method. So technically I will draw a section at that point. It means when I took that section, that's the 5 kilonewton is not included in that section. I have only the 31.25 and the weight of the UDL and replacing that section we just got here with the shear force will be value V. Therefore, will be this 31, this will result for you at 10.5. So you have 31.25 minus 10.5. This will reduce to that point 20.75. So that line is here. Now, we got another force, is dropping that, the 5 at that point, we have 5 kilonewtons going downwards. So this will go 20.75 minus 15.75 till this point. Now, I have again the impact of UDL will stop at that distance. So this from here to there, how can I do it? If you see carefully in the second diagram I'm representing for you guys, I need to take another section at another point. So let's take this section this time around this edge, this end. Okay, so that section similar to here. So what do you have? The distance completely is 5 meters. You have 5 kilonewtons, and you have the UDL, which is 7 times 5, 35. So you add these equations together, you have a shear force at that point is equal to what? 31.25 minus 35 minus 5, it's equal to minus 8.75. So the value here will drop to negative, so minus 8.75 till this point. So that's where you have 2 points, you connect them with a line going in slope because it's going downwards, so you put it in the negative. The negative is indicating for me the direction of the slope. It's going downwards, so I'm in the negative position. Now, since we finished that side, now the rest is straightforward. Since there is no forces from here till the 5 kilonewtons, so I will go in straight line. Now, this is going negative the 5 kilonewtons, so it will be minus 8.75 minus 5 will be minus 13.75. And after that, I will continue as well with no force from this point to that point till I will close it down because I have another support reaction is equal to 13.75 going upwards. If you see carefully, at that point I noticed that, hey, I'm going good because if I have at this point minus 13.75, so I'm closing with 13.75 positive and gets to 0. So that's indication for me here I'm going in the right direction. So this is using the section method to find the shear force along this beam, this example. Let's try now how can we find the bending moment. So I keep the shear force diagram here because I need it and I need to go and discuss it step by step. So step 4, bending moment diagram, BM diagram using the area methods. I sketched exactly the same thing. I recommend you do it underneath it, but because of the space I'm doing it on the side to keep myself away. So I just copy the disconnected lines so I can work around them. So what do you have here? We need to find the area for each part. So in the first area here, what we have? We have a triangular and you have a rectangular. It's very easy to find the distance. So to find this one, this height is 31.25 minus 20.75, and then you find the value and you apply it. So what we do it, half the base, 0.5, 31.25 minus 20.75 times what the width is, which is from that distance, if you look to it, is 1.5. That's the area for the first triangular, plus 20.75 this rectangular times 1.5. You get a value of 39 kilonewtons meters. So I put the BM in kilonewtons, I put the number here 39. Now for the second step, what do we have? We move to this triangular. It's very difficult to find the area for this triangular and the area of that one because we don't have the distance x. What we know that this distance represents for me very clearly, if all of it is 5 minus 1.5, the remaining is 3.5. So let's assume this one is x and this one will be 3.5 minus x. I'll explain it in class in more detail about this one because this is very, very important. So what we do, we use the trigonometry theories. X divided by that distance, which is 15.75, is equal to what? 3.5 minus x divided by 8.75. Because they have the same angle, therefore they should have the same ratio for it. You arrange the equation, you find x value is equal to 2.25 meters. So after we determine the x values, we need to find the area for this part. So how we do that? Half of the base times the height. So half the base is 2.25 times the 15.75 equals 17.71. So that's area. We'll add it. Now, because I stop at 39, adding 17.71, I'll get 56.71. Now, I continue with the next step. After finding this one, I need to find this area. And if you see it's negative, so I should predict to get a negative answer. So the area for that part will be, again, half of the base, the base is 3.5 minus x, 2.25, times negative 8.75, I will get minus 5.46. Minus the last value of the moment we found, 56.71, that will end up with 51.25 kilonewtons meters. We reached to here. Because we have a UDL, you see I'm using curve. So I'm using curve here, I'm using curve here, I'm using curve here. Now when I move to the other areas is just a rectangular, then I use only a slope or gradient lines. So to find this area is very easy. Minus 8.75 times the distance, which is 3.5, and that will give you a value of minus 30.625 plus the 51.25. This will remaining 20.625, and that's I reached to this point now. So from this point I need to find this area. So it will be minus 13.75 times 1.5. that will give me minus 20.625. Therefore I will close the diagram with 0. Now if we ask you which one is the maximum bending moment, the maximum bending moment, it's equal, maximum bending moment is equal 56.71 kilonewtons meters. This is the maximum bending moment, and usually occurs when the shear force is equal 0. It's happening actually at the point, no, sorry, it's usually happen at, if you look too carefully to it, it's happen at this point. That's the maximum bending moment we're getting at this location. So it's not really when the shear force is equal to 0. So that's the location where it's giving me 56.7 kilonewtons meters. And you just need to highlight this point has the maximum bending moment. Where is the shear force is equal to 0? At that point. You see it is passing at that point. So about a distance 1.5 plus 2.25, you get a shear force equal to 0 at that location. And this will sum up with this question. So hopefully I will see you in the class and explain the rest how to determine these angles. Thank you very much. I hope you enjoy the video. See you.